What determines the shape that a company uses for a soda can? Why this height? Why this radius? Why this diameter? What determines the shape of a soup can? Same idea. For some reason they're kind of similar. Why did they choose this shape? How about how about a cereal box? Why, to fit this amount of cereal, is it chosen with this height and width and length? What is the best shape? That is a question that is very useful in lots of applications. What is the best shape? Or in mathematics, we say, what is the optimum shape? How do we optimize the material that we want to use? The material that we need to fill this with, maybe the metal that we need to make the can or the cardboard for the box. How do we best use the material and save money, right? Companies are in the business of making money so they can pay people, so they can eat and live and all that stuff. But what's the best way? And that's what we're going to learn in this lesson. We're going to talk about optimization. How can we use calculus to optimize and find the best solution to a problem? And that is called optimization. And calculus is the perfect tool. We'll put this in the box here. Okay, calculus is the perfect tool to find the box or the can or the size to make this the best, to answer questions in an optimal way. So we're going to look at a few applications here where we see that derivatives can be used to solve these optimum problems. Well, the key here is, as we've seen, derivatives can find maximums and minimums, and they find that because we know that the derivative is 0 at these points, right? So a lot of times we're looking for problems that we're trying to find the least amount or the greatest or the highest or the lowest. When we see these words, slowest, fastest, we know that these are an extrema, all right? And we're looking for the optimum or the optimization problem is what we call these here. So, the first kind of problems involve volume and area. So our situation here is we want to maximize the volume of a box. So a manufacturer wants to make a box. It's an open box. So that means it's got no lid here. And we've got a square base. That's going to be important. We know we have a surface area of 108 square inches, and we want to find the dimensions for the maximum volume there, all right? What is that maximum volume? All right, so here's some steps. We're going to start by finding some key equations that relate the problem. Okay, so we got a primary equation. That's the one that we want to optimize. What are we really going for? In this case, we're going for maximum volume. Okay, so we know a volume of a prism, a rectangular prism, is length times width times height for a rectangular prism. If you have other shapes, you got base times height in general. Now, but this one is even a little more specific here because instead of length times width, we have x times x. So I'm going to swap out that length times width with an x times x, or we could do an x squared. All right, x squared times h. All right, so now that's our volume equation, x squared times h for this box. Now we've got a second equation, and that's the area. We know something about the area. We've got a surface area that is 108 inches. So all the area of these sides, there's 5 sides, bottom, and then the 4 sides, all right? That is going to be a surface area equation. So our surface area is all those together. We've got the bottom, which is x times x, or x squared. And then we have this side right here, which is x by h. We've got this side, which is going to be x by h. And in fact, all 4 of the sides are x by h. So it's not about memorizing or thinking back to your geometry necessarily, other than how do you find the area of a rectangle. We've got to realize we have 4 sides and therefore rectangles, 4x times h. All right, so that's the surface area. Well, now we also know one more thing about this. We know what the surface area is. And I've got 108. So we can swap that out. We know the surface area is 108. Let's go ahead and put that in there. So here we have an equation that relates x and h. And here we got volume equals x h squared. So what we're going to do is we're going to solve this and substitute there. Okay, so you could solve this for x, but that'd be a little tricky because it's in two places. Here it's squared, here it's not. So it's going to be easier to solve this for h. So let's solve this for h, and then we'll substitute it into the volume formula. So if we subtract x squared over from both sides, I'm going to have 108 minus x squared, and then we'll need to divide the whole thing by 4x. All right, so I'll go ahead and write that step out. 4xh equals, so divide everything by 4x. We've got 108 minus x squared all over 4x. Don't try to simplify it. That's good enough for the moment. So, all right, so h equals that. Well, we're going to go ahead and substitute there. Okay, and then we'll get a volume formula. And we'll substitute for h. So we have volume equals x squared times h. But what is h? We just found it. It's 108 minus x squared all over 4x. All right, let's clean this up here. This x squared, we'll cancel one of these, this x I should say, we'll cancel that one of these x squares, just leaving x. And then we should divide this by 4, so we've got volume equals, if we take, well, x over 4 times 108 minus x squared there. All right, and if we distribute this out here, we're going to get something like volume equals, I think 4 goes into 108, that's 25 plus 2, 27 times. Okay, x, so we just distributing this out here, and then we'll have minus x cubed over 4. Now we want to maximize that, so we want to find the critical values. We know the maximum of this is a derivative. So we need to find v prime. Well, v prime is going to be 27, and that'll be minus 3/4 x squared. Okay, where do we find maximums? That's critical values. Remember that? Okay, so critical values, and also we want to remember this. Let's note this. Don't forget the endpoints. What are the endpoints here? Well, what is the smallest and the largest, in this case, x could be? All right, so we could have a super skinny box where x is 0. All right, that would be a pretty, it wouldn't even hold anything, of course, but 0 is the smallest that it's going to be. Okay, and then if this was just a flat rectangle, it had no height. If there was no height there, then it would just be a square, and that square would be 108. So we'd have the square root of 108. And it would just be a flat piece of paper that won't hold anything. All right, so those are our endpoints of this interval. So we need to set this equal to 0. Equals 27 minus 3/4 x squared. How about we subtract 27 from both sides? 27 equals negative 3/4 x squared may multiply by 4/3. Remember that? It's been a while since that algebra 1, but multiply by the reciprocal would be a good idea here. That's going to be, it looks like 36. 27 divided by 3 is 9 times 4 is 36. So we have 36. Oh, by the way, this is a negative because I subtracted from both sides. So it's positive 36 equals x squared. And we can solve that square root. And we get a value of x equals plus or minus 6, but we don't need the plus and minus. We're just going to go for the positive version. So now we want the dimensions. The question asks for the dimensions, so let's get the height as well. Height is going to be 108 minus 6 squared all over 4 times 6. And so this comes out to be 3. So the box is going to be 3. And what's our units here? They're inches. So the box is going to be 3 inches by 6 inches by 6 inches. That's the size of the box. All right. Great. So that will give us the maximum volume for that surface area. Okay. All right. Well, let's do a similar problem, but talking about area here. So Old MacDonald had a farm. Did you say E-I-E-I-O, right? Okay. And on that farm he had some pigs, E-I-E-I-O, right? Okay, you know this story. You've heard it before. And then on that farm, he's got some fencing. He wants to make a pig pen, all right? And he's got 200 feet of fencing. And he wants to make a pen for the pigs with the largest area. Okay, keep in mind, that's going to be our primary equation. So we have two equations. We've got our primary. Our primary equation is going to be the area. That's what we're trying to maximize. Area equals, this is length times width. It's a rectangle, right? Now, this problem's a little incomplete. It actually doesn't say it's a rectangle, which could change things because actually, if you want to get maximum area, a little side note, if you want maximum area, then you can use any shape. Do you know what the best shape would be? The best shape would be a circle. All right, but we're going to keep it, we're going to assume it's a rectangle. I'll cheat, okay, and say that's going to be a rectangle. Okay, so we got length times width. That's our area, all right? Now our secondary equation that kind of we know something about is going to be a perimeter equation. We know we have 200 feet of fencing. That's what's limited. So we know the perimeter is 2 times the length plus 2 times the width. If you remember, that's how we find the perimeter rectangle. And there's some other forms. You could do L plus W times 2. That would work also. And we know the perimeter in this case, the perimeter is 200. So 200 equals 2L plus 2W. Now, what we want to do is we want to solve this for L or W, substitute, and then we're going to use calculus to find the maximum area, the largest area, all right? So if we divide everything by 2 here, we get 100 equals L plus W. And so you choose. It doesn't matter which one you pick for, which you solve for, I should say. Okay, if you subtract W, we get L equals 100 minus W. So our area equation becomes, if we substitute, 100 minus W times W. And we can see that's a quadratic equation now. All right, so we can distribute here, and we've got 100W minus W squared. We want to find the peak of that, which is hopefully you're thinking that's the vertex, right? I've done that before. Yeah, that's kind of an algebra 2 problem there to find the vertex. But let's use calculus here. All right. So to use calculus, we want to find A prime. We want to maximize this. Well, A prime is, we've got 100 W is going to become 100 minus 2W to the first. And we want to find the critical values, the largest points, okay? So we want to set that equal to 0, okay? All right. Now, solving that, we got 100 equals 2W, and divide by 2, and we get 50 equals W, all right? There's our width, and so our length, we found out right here, the length is going to be 100 minus W. So the length is 100 minus 50, which is 50. Okay, so the pen with the largest area is going to be a 50 by 50. Okay, so the largest area will be given by 50 by 50, and that gives us 200 feet of fencing. Okay, now, then that's going to give us an area of 50 squared, which is 2,500 square feet. That's the largest area. Now we should check the bounds here, all right? We could have a super skinny rectangle with that is like a 0. We've got 200 feet of fencing, so we could have 0 by 100, right? Or 100 by 0. So, well, what would the area be? That'd be no area, all right? So we should stop and think about that in this problem. Those don't make sense, but okay. So the largest area would be a 50 by 50. So remember, we want a primary equation and a secondary equation. The primary equation is the one that we're trying to optimize. The secondary is that helper fact that we know.